Okay, thank you for having me today. So I'm very happy to be here. This is my first astronomy on tap in Leiden. Let's hope it goes well. So I'm going to talk about the origins of planets and moons. And here you can see a very nice picture made by some people at the Space Science Telescope Institute in the US of a planetary system that I detected already way too long ago. But I will tell you about it later. Let's see. So it was already came by this year tonight, about how planets and stars form. It happens in sort of 5 big phases, where on phase 1, which is on the top left, is you start with a giant cloud of gas and dust in interstellar space. Well, these clouds are super heavy. However, and that heaviness causes the cloud to collapse due to gravity. And in that large cloud, you can have dust clumps and gas clumps, and they will form stars. So in the beginning, you'll get dense cores, and those are precursors to star formation. Well, these clouds, they're not still. They just don't fall and collapse into a point. But there's some kind of rotation speeds, and that can be primordial, that can be caused by other things, but there's some type of rotational force. And because of that, these stars don't collapse into a point, but they collapse into a disk, as you see here on the bottom. It's sort of similar to how you make a pizza. When you make pizza, you throw it in the sky, or not in the sky, in the air. It flattens into a flat pizza. At the end of star formation, and this is also like the most important stage for planet formation, because it's in this disk of gas and dust, is where planets form. So that is very crucial moment to understand if you want to know how planets form. But then at the end, the star blows away all this gas and dust, and then we're left with a mature solar system, as like our solar system as we know it now. Currently, most of the planets have been found by the transit method. It was already said in the quiz. And the transit method mainly finds planets in this, or like not mainly, it's like almost all planets are found in this final stage. And it means it's very difficult to actually learn how planets form. We only know the end result and not the pathway through planet formation. So, my talk today will be a little bit about how can we actually analyze and learn about planet formation. We need to use a completely different technique than the transit method to do this. So I'm going to talk about my favorite methods to do exoplanet imaging and exoplanet characterization. It's also 99% of the work that I do. And that's direct imaging with the largest telescopes on the ground and in space. So here you can see a picture of the Magellan Clay Telescope, which is a US telescope built in Chile. And it's one of the telescopes that I use the most. So I generally spend like 1 or 2 months a year there. So it's a lot of fun. And then we use these telescopes to actually look for planets. But one of the problems here is that these telescopes are on the ground, they're on Earth. And that means we need to look through the Earth's atmosphere. The Earth's atmosphere causes stars to twinkle. And that twinkling is actually very detrimental to our observing. It reduces our resolution and it makes it very difficult for us to search for planets. So what we do is we use a technique called adaptive optics. Let's see if it goes further. So due to the twinkling of the star, we see a star constantly moving around, creating all kinds of spots, and it's super annoying. So we use adaptive optics. In adaptive optics, there's light coming in from a star, and it's sent to a special sensor. This sensor actually measures the distortions that are caused by the atmosphere, by the turbulence, and it calculates the optimal shape to correct for that distortion. And then we have a special optical element called a deformable mirror. That's a mirror that can change its shape. You can see all these magnets that are changing the shape. So from the pre-calculated shape, we can actually adjust it so that the light that comes in with an error returns flat, and it's actually corrected now. And after that correction, we actually regain high image quality, and we can actually start to search for planets. So here you can see it in real life. So in the beginning you see a lot of turbulence, and in the end we turn on the system and we get a nice sharp image. It's a little bit saturated, but it's still a nice image. I will do it again. So at the beginning you see all the turbulence, and then we close the loop, and the star is sharp. And the one thing that you can see here is now there's an additional star, which you originally could not see. There's a couple other spots, but those are from the instrument. So this is adaptive optics. We need to do this correction 1,000 or 2,000 times per second. So it's really at really high speed that we need to control the atmosphere. It's annoying, but we'll have to do it. So then, we have recovered our star, we have done adaptive optics, we regained our resolution, and now we're searching for planets. So in this image, there's a firefly that we're trying to search for. And this is actually very similar to how we're trying to search for planets. Planets are extremely faint compared to their star, and it's very similar to searching for a firefly around a lighthouse. Except for that this is like 100 to 1,000 times easier than searching for a planet. If we had a special trick to get rid of the light from the lighthouse, we could actually very easily see the firefly over there. Well, we cannot go to a star and ask it to turn itself off. So we built specialized instruments called coronagraphs that are used to block out starlight for us to search for planets. So interestingly, a coronagraph was originally used to study the corona of the sun. And the corona is the crown of the sun, which is also the same word that corona was used for the COVID virus. So it actually has the same origin. But if you use these techniques together, we can actually see exoplanets around other stars. So here you can see the system, it's called HR8799. It's one of the most famous systems in direct imaging. It actually has 4 giant planets. So if I turn on the movie, you can actually see the 4 giant planets orbiting their host star. And every time I see this movie, I think it's super cool, because here we can just see a movie of a alien solar system with the planets really orbiting. So the planets are of course here, there, and it's a little bit further out. So this is the technique of direct imaging. We use giant telescopes to resolve planets from their host star, and then we use coronagraphs to block out the starlight to search for faint structures. And now, instead of doing this with older systems, so this is an older system, because as I told you before, young systems have these disks. This system doesn't have a disk anymore, so we want to look at younger systems. If we use these kind of direct imaging instruments and look at these young systems, we see this huge variety of circumstellar disks. So these are the disks that are the sites of planet formation. Well, I don't know about you, but it's very difficult for me to find these planets. There's all these structures, all the light, and now it's actually very difficult to disentangle the light from the disk from the light of the planet. So we were quite happy when we saw these disks and we were trying to search for planets, but it was actually very difficult. And it's because of all these interesting structures that we see in the disks around the planet, around the stars. So we needed to do something more. So this is an artist's impression of a young planet. So a young planet also has a disk around it. So it's disks all the way down. And these are called circumplanetary disks because they're around the planet. And one of the things that you can see here are these funnels. So there's these streams of material that fall on top of the planet. And that causes a process that's called accretion. So during accretion, planets are actually growing their atmosphere and they're growing their mass. And the material is transported through these funnels on top of the planets. And that causes a very specific signal in light. So a very specific wavelength gets emitted. And that's not emitted by the circumstellar disk. So you can actually search for this specific feature in the light that actually disentangles it from the star. So I tried to do that with this telescope, the very large telescope in Chile, with the MUSE instrument, which you can see on the lower left. It's a huge instrument, really big, really compatible with a very large telescope. But this telescope does adaptive optics, and it actually uses these lasers. They're super powerful lasers, shoots them into the sky, and it actually creates fake stars. And these fake stars are then used for the adaptive optics. It's very interesting. But with this system, in 2019, I was actually able to find 2 planets. So here you can see them in the red box and in the purple box. And then if we look at their spectra, so their the intensity as function of wavelength, we can actually see that there's a very specific peak at the wavelength that we expect. Because these planets, when they're accreting, the majority of the signal is actually coming from very, very hot hydrogen. And these lines that we're seeing here are exactly at the location of hydrogen. So what we're seeing here are planets that are being formed. They're getting their atmosphere together. They're eating all that mass, all that and gas together. And to show you why this technique really helps us is if we compare it to the infrared images. So here we see the 2 planets again, this time with a slightly longer exposure time. They're in the system called PDS-70. And the original, the detection paper, showed the image on the right, which is in the infrared, where we also see the disk. So here, you can definitely see like the first planet they discovered, which is PDS-70b. But there's also a lot of structure around it from the circumstantial disk. Now, if we look on the left, there's definitely one of the points is associated with that special color. But the other point we could only see by knowing that there was something going on here. Because the point here is very close to that disk, and it's for us difficult to disentangle whether or not it's disk-like or it's an actual planet. So using that new technique where we look at that very specific hydrogen signal allowed us to disentangle the planet from the disk. Sorry, this was a blank slide I accidentally added. So, going to the next slide. So after that, we also looked at it with ALMA. So here you can see ALMA, it's the Atacama Large Millimeter Array. And with we, I don't mean me included, but we as a community, because I was not involved in this research. And this is a large interferometer at sub-millimeter wavelengths and millimeter wavelengths. And it's really good at searching for dust. So it also looked at PDS-70. And what we saw, first of all, we saw the disk around the star, but we also got a very strong detection of a disk around the planet. So this was actually the very first time we detected a disk around the planet itself. And if we look at the animation, so there's of course a nice video. So here we have the planet PDS-70, see? We zoom out and then we see around the planet there's also a circumplanetary disk. And in this circumplanetary disk, what we think as astronomers is that those are the sites of moon formation. So if you want to figure out how moons form, we need to search for these circumplanetary disks, which we now can for the first time. So it's great, we found actually the first protoplanets. So these, what I call protoplanets, are planets that are being formed, or you can also call them baby planets. And then, well, we spent years observing with the VLT, searching for more, and we did not find any. We actually observed almost 100 systems. We didn't actually find any new ones. Up until we started with the MEGIOX instrument. So here you can see me on the left doing very, very important work. I was adding Ziploc bags to the optics to protect them from dust for transportation. I look very serious doing it. And on the right you can see it installed at the telescope. So this instrument, MEGIOX, is developed at the University of Arizona in the US. And it's actually specifically designed to search for these protoplanets, for these young giant planets. And we were actually successful. So here's WISPET 2b, which is a new planet we actually found 4 months ago. So that's really special because it's only I would say the second protoplanet, maybe the fourth, it depends on who you ask, because some people found things they claim are protoplanets. I don't trust the results too much, but yeah, you can always claim something. But this is a very clear detection of a companion in a disk, again, that's carving a gap. But this is in infrared light, this is in scattered light. So with MEGIOX, we looked at it in the hydrogen filter again, that's searching for that very specific accretion signal, and then there it is. we detected it again in hydrogen. So this planet is definitely accreting and is growing its atmosphere. So it's also very young. So of course we did try to do more. We found another one, 2MJ1612b. It's another one that we found. It's very exciting that we're now finally, with this new instrument, starting to find them one after another. Because this is actually what allows us to understand how planets form, how these giant planets get their atmosphere, how they get their mass, and how they interact with the circumstellar disk. And those are all the processes that we need to understand how planets form. So what's the future? The future of ground-based telescopes are like the next generation of telescopes. On the left, we have the European Extremely Large Telescope. Of course, extremely large because the Very Large Telescope already existed. And on the right, we have the Giant Magellan Telescope because the Magellan Telescope already existed. Both of them will be huge. So the Giant Magellan Telescope will be 25 meters from one side to the other, and the Extremely Large Telescope will be almost 40 meters across the prime beam mirror surface. So they're huge mirrors. Sadly, the image on the right is an artist's impression, it's a rendering, while the image on the left is actually an image. So that's a photo taken last June. So the ELT is currently being built. GMT is still a little bit in a funding situation. It's a situationship. However, if we look at what these planets or what these telescopes are actually promise us, is on the right you can see me looking at PDS-70 with a very large telescope for 16 hours. So this is using 16 hours of open shutter time, while with GMT we can get this result in 1 minute. So the difference between the aperture really, really matters. Bigger is better in astronomy. So that brings me to the conclusion. So in 2018, 2019, we found the first 2 protoplanets, PDS-70b and C. Now in 2025, we found 2MJ1612b. I'm amazed that I remember that. And then there's WISPET-2b, which we also found. So we're now finally slowly starting to detect these new protoplanets that allows us to understand how planets actually form. And hopefully with the future telescopes we will be able to do this even better. Thank you.
Thank you. Do we have questions for Sebastiaan? Hand straight up there.
I was wondering, what makes this instrument that you built so good at detecting planets compared to the other ones?
Sure. So the question was, what makes this new instrument so good at detecting these protoplanets compared to other instruments? Well, it's all in the adaptive optics. All the other instruments are actually made in such a way that the adaptive optics works well at infrared wavelengths, so at longer wavelengths, while this hydrogen gas signal actually occurs at shorter wavelengths, at optical wavelengths. And the shorter the wavelength, the more difficult it is to have a high-performance system. It becomes exponentially more difficult and exponentially more expensive, actually. So you actually need better technology. So this is a newer instrument with newer technology, allowing us actually to do better at the shorter wavelengths compared to the other instruments. So it's actually it's just better technology.
Right at the back. Yep.
How far away are these baby planets?
So the question is, how far away are these baby planets? It varies a little bit. To be honest, I don't have the exact numbers in mind, but I know PDS-70 is at, oh, I should know this, I wrote this so many times in the paper. What was it? Something like 110 or 120 parsec. So that's, I don't know, 400 or 500 light years or something like that. WISPET-2b is at 118 parsec, so it's a little bit further away. I think J162b is also at a similar distance. It's also about 100-150 parsec. And that's because a lot of these planets, they form actually in what they call star-forming regions. So those are sort of stellar nurseries. So those are the places where new stars are born. And they all are roughly at this distance of 100 to 200 parsec, so somewhere between 300 and 600 light years, or at least the nearby ones that we can observe well.
Yeah.
Yes.
Yeah, so I was wondering, how does our atmosphere even distort the light from the stars?
Yeah, it's a very good question. So how does our atmosphere distort the light from the stars? So in our atmosphere, we actually have hot pockets of air that are moving up and down. Those are also the hot pockets of air that create our weather. And when light travels through it, it actually gets distorted by those differences in temperature. So you actually have variations in temperature while the light is traveling through the atmosphere of the Earth, and that causes distortions. And that messes up our light. It's very cool, like you have the light from this star, it travels for like tens of thousands of years, and then in the last 2 seconds, when it goes through our atmosphere, like the last couple of milliseconds, it gets completely destroyed. All these photos, they try their best, and our atmosphere is in the way.
How do we go from observing the protoplanets to understanding better the planet formation?
That's also a very good question. How do we go from detecting these protoplanets to understanding planet formation? So one of the big aspects of planet formation, and one of the things that we don't understand well, is how planets interact with the circumstellar disk. Because that's a crucial aspect of their formation. Like, how does the material actually go from the disk to the planets? How does that merit? And that's actually what we try to understand here. Like, how much material do they grow? Like, how much do they grow per year? What is the actual physical process that is responsible for transporting the material from the disk onto the planet? Those are all things that we can actually analyze from data like this. I had the original picture. Hopefully I can go back. Where's the nice picture? Go back. Go back. A little bit further. I have to go back really far. So, more. Yeah, here it is. Stay. So, here you can see you have the circumplanetary disk, and there's material that goes from the disk onto the planet. So here we have a process that we call, this is a process called stellar cohesion, where you have these funnels that connect from the disk on top of the planet. But this is just one of the processes that could maybe transport material from this circumplanetary disk on top of the planet. There are also other ways that the material could go to the planet. For example, it could directly fall on top of the planet, or the disk could actually feed, like horizontally here, it could feed the material to the planet. And disentangling all these different kinds of processes, they leave different fingerprints. And we're trying to figure out like which of these processes is actually responsible. So at the moment we have a lot of theories about how this material gets transported, but we have very little observational evidence for any of the different processes. So by looking at these different planets, we can actually start to figure out like which process is responsible for carrying the material on top of the planet. And then we know how they grow. And if we know how they grow, we can actually start to use that in our simulations and correctly predict the evolution. So that's how we try to do that.
So this method that's using hydrogen, is that only spotting this method that it's getting material on there, or some of these other methods where it might be going in directly? Are you not seeing planets that are being formed by that?
In theory, I think we can like all the 3 methods that I just mentioned, we can actually detect them through the hydrogen lines, because this occurs when the hydrogen gets really, really hot. And whenever the material gets deposited onto the top of the planet, it gets really hot, because you can imagine like you have this parcel of gas, it's flying along, and at some point it suddenly hits the planet. And that's very strong shock. It heats up the gas, and that causes this specific light. But all the different methods, they create a different temperature. And because of the different temperature, you get a slightly different signal. So you can actually disentangle the different methods from their temperature.
How do you choose the systems you want to
How do you choose the systems that you want to observe? Yeah, that's a very good question. We have a lot of fancy methods, and those fancy methods were used to select stars to search for these kind of planets. And we use them for surveys. So for example, with a very large telescope, when we built the new exoplanet imaging instrument, we had a big survey. It was called the SHINE survey. And with that, we did a very, very careful analysis of like, what are the most interesting stars to look at? In the end, that led to a 1% yield. So only 1% of the objects we looked at had a planet. It was very bad. In the end, what works almost best is just randomly picking a star. It's very sad.
I think the question back there was first.
How much better is it to use a space telescope compared to a ground telescope when looking for exoplanets?
How much better is it to use a ground-based telescope or a space-based telescope for searching for planets? Actually, that's an unresolved question. At the moment, what we see for direct imaging, for doing it like this, a bigger telescope is better. So currently on the ground, telescopes are bigger. However, space telescopes are more stable. But like for example, James Webb is a little bit smaller than our ground-based telescopes. If I can go back, yes. So here you can, for example, see all kinds of data that we took from the ground. Oh, let's see if I can get the video to play. But if you look here in the middle, you can see that there's a lot of stuff happening. And that's all actually residual effects from our image processing, because we were not able to get rid of the star completely. There's a lot of stuff left. And we do that with advanced image processing. We try to remove some of the more starlight to reveal the planets. And what is true is that for space-based telescopes, this is easier because they're more stable, so we can much better post-process them away. However, ground-based telescopes are still bigger and bigger wins. So there's a bit of an unresolved question there. Is like, which one is better? Is it better to do better image processing at the end, or is it better to have a big telescope? So I'm mainly a ground-based person. I don't do a lot of space-based telescope stuff. So I would say bigger is better, so let's go for the ground. But other people might have other opinions.
Hi, you said you might have seen a moon forming in the EF-70 system. I was wondering, how do you actually determine whether a moon is forming in a certain planetary system?
Yes. How do we detect a moon is forming? Yeah. At the moment, we've never detected an exomoon. It's one of the things that we really want to do in our field. Sometimes there are papers or people that claim they've detected an exomoon, but then it's debunked a couple of weeks later, because moons are, like planets are really difficult to detect, and the moon is even smaller than a planet, so it's even more difficult. So currently what we're finding, and I think that's a really something from the last couple of years, is that we're actually finally detecting signals of certain planetary disks. So we can finally detect the sites of exomoon formation. And we think, based on the fact that like lots of planets in our own solar system have moons, that most planets actually form with moons. It's sort of like the star systems. Like stars, they form mostly in binaries, and we think that planets also form mostly with something around them. So we think if there's a certain planetary disk, it could be a possible site of exomoon formation. But we have never detected an exomoon before. We're trying.
See one more at the back.
What makes the initial, like, in the early days of the system, what makes the initial cloud collapse to this?
What makes the cloud collapse to a disk? So if I would give a really astronomy-based answer, I would say magnetic fields. But we just assume like when these clouds, they're always dynamic, they're moving around. So at some point, due to gravity, they start to collapse. There's a critical mass, so a critical density, before it starts to self-collapse. And when it meets that critical density, it just starts to do this. So you have different, like in the Milky Way, if you go around, there are some places where you have like these very dense pockets of gas, and that's where it happens.
We have a question down here.
Yeah, I was wondering about the optics. Do they have a model of atmosphere, or do you have weather observations that help you adapt the optics, or how do you actually?
So a good question, how do we do the adaptive optics? Do we have models of the atmosphere? So actually during this process, of adaptive optics, we actually have a specialized sensor that's called a wavefront sensor that constantly at 2 kilohertz, like 2,000 times per second, actually tracks the distortions of the atmosphere. So that's this sensor. So it constantly tracks and measures the distortions. And based on that, it actually knows like how do we need to choose the correct shape for the deformable mirror to compensate for these effects. It's very difficult because you need to do this 2,000 times per second with starlight, and starlight is quite faint. So you need to be super, super, super efficient with the light that's coming in. You need to be super, super sensitive. Otherwise, you're throwing away a lot of the signal. Yeah, so we all have sensors that measure what's happening. Because like you see here in the beginning, like it's turbulent. So we can actually sort of at very high speed, we can track what's happening to the star. We are trying to use weather patterns and weather forecasts to better predict when we do certain observations, so that we can be more efficient. Because in certain atmospheric conditions, the adaptive optics works better than in other conditions.
It's nearly time, but if this may be time for one more question, because I thought I saw a hand going up, but okay, yep, go on then.
Yeah, so given that most planets are pretty stable already, I was wondering, do we know how long that planet formation process actually takes?
How long does the planet formation process take? It's a bit of an unknown question because we don't know very well how planets actually form. We have a couple models. We do know a rough upper bound, and that rough upper bound is about 10 mega years, so 10 million years. And that's because after 10 million years, the star blows away the disk. And when the disk is blown away by the star, there's no material anymore for the planet to form. So within 10 mega years, the planet must form. Otherwise, there's no way for it to grow anymore.
Is that like short in astronomical terms?
Well, yeah, I mean, I would say that it's quite short. Like our own solar system is about 4.5 giga years. So it's 4.5 billion years, so that's like 450 times longer than the planet formation time scale.
Okay, let's thank Sebastiaan again.